In this module, we're taking a look at sections 8.1 and 8.2. The techniques are introduced in 8.1 and application areas are discussed in 8.2. And if you want motivation, you'll find more motivation in 8.2. If you want an understanding of what the techniques are, you'll find that probably best described in section 8.1 of your textbook. I'm putting them together because we have techniques to learn, and I'd like you to be motivated by the application areas. I believe that you'll see that the application areas are very broad, and they may have been introduced to you already if you've taken a class in remote sensing, or if you've taken a course in stress analysis like mechanics of materials. These topics will actually be very familiar to you. But you may not know them with this language and may not know the techniques that we're going to be learning in this module. But I hope you'll find them valuable in your career. I was surprised by how often I've had to deal with eigenvalues and eigenvectors, usually without calling them that. So in chapter 8 we take up this issue, and the issue is going to come up with many different square matrices, and that's one of the important things to remember, is that you cannot find the eigenvalues or eigenvectors of a matrix that isn't square. And when we start off, we're going to use the variable lambda, and the values of lambda that and the non-zero vectors x that satisfy this equations are what we're after. And the values of lambda will be known as eigenvalues or characteristic values, sometimes also known as principal components. And the values of x, these vectors that satisfy the equation above, will be known as eigenvectors or characteristic vectors. And only non-zero vectors are of interest to us here. One of the things that's useful to note is that we never actually find our eigenvalues or eigenvectors using the expression shown on this slide. But if you ever have a candidate, or if you want to check your solution to see if it works, you're going to find it very useful to remember to use this equation to check your work. So this expression isn't terribly useful for finding eigenvalues or eigenvectors, but it is very useful for checking to see whether you have them correct. So to actually go about this process, we need to define the characteristic equation, and find the eigenvalues of a square n by n matrix. We establish this characteristic equation, which is a polynomial of order n, where we are using the determinant of the quantity matrix A minus lambda times the identity matrix. Now, what's the magnitude of the identity matrix? It matches whatever A is. So if A is a 2 by 2, then we'll use I that's a 2 by 2. If A is a 3 by 3, then we'll use the identity matrix that's a 3 by 3. We solve for the roots of the polynomial that we obtain by finding this determinant in order to find the eigenvalues. There is at least one, and as many as n roots for this polynomial. The different cases will come up best when I discuss them in the context of different example problems. The eigenvectors are the non-zero vectors, which then satisfy the expression quantity A minus lambda I times x is equal to the zero vector. And so first we're going to separate this into two tasks. First we find the eigenvalues, and then we find the associated eigenvectors. Let's start by looking at an example. That expression that I gave you before, determinant of the quantity I minus lambda identity matrix for a 2 by 2, that expression just works out to be this, where you see the determinant on top here. This expression here is what we're going to take a look at, which we can expand by the matrix addition definition to be involve that only the diagonal terms have this lambda or the minus lambda applied to it. And now it's time for us to calculate the determinant, which we get simply by taking these two terms multiplied by each other minus these two terms multiplied by one another. And with that we get the expression a11 minus lambda times a22 minus lambda and minus the a12 a21 term. And this is simply a polynomial that we need to find the roots or zeros of. Usually this is not the form that we want to work in, but it does tell us what we've needed to do in order to define what's known as the characteristic equation. So that's the characteristic equation for the matrix A. And if I continue with this, well, it's probably easiest to consider a specific example. Here's a 2x2. Given the matrix shown, find the eigenvalues and the eigenvectors. You're going to see that this is a multi-step task, and I'm going to work this example all the way to the end, and it's going to take 3 slides to get it all done. So first we set up this determinant with A minus lambda times the identity matrix, which is a little bit cumbersome when we know that all we got to do is subtract lambda off each of the diagonal terms and then find the determinant. So I'll just go right to that step and show you that we're trying to find this determinant and set it equal to 0. And for our specific example then, we can evaluate the determinant to get this expression. And when we multiply through those two terms and expand that, we still have to subtract the 1, so we take the 4 minus the 1, and that leaves us with 3 as our constant. And now here's our characteristic equation at the bottom, and usually you'll be able to spot the roots if you have strong skills in dealing with finding the roots of a polynomial. You're going to not mind this task very much. You'll definitely need to know the quadratic equation, but in this case you can probably factor out this polynomial at the bottom here and identify that one of the roots is 3 and the other root is 1, and that is indeed the case. So you'll see when you expand this out, the characteristic equation is shown, and you can factor that into 3 minus lambda, the quantity 3 minus lambda times the quantity 1 minus lambda, and thus we have the roots of the polynomial are 3 and 1. Those are known as the characteristic values or eigenvalues of the original matrix that we were given. For each of those eigenvalues there is an associated eigenvector. There's a directionality associated with those terms, and to find that we now need to evaluate the expression a minus lambda I times x, and we do that twice. In this case, for the two-dimensional case, we have to apply this twice. In general, you need to apply this task for every eigenvalue. There is an associated eigenvector, so finding the eigenvalue just gets you started. You now need to find the associated direction with that eigenvalue or characteristic value. So we'll start with the first one. So with lambda equal 3 from our example, we just take 3 off the diagonal terms, and then we set up this system of equations that we get. So here's where we're taking 3 off the diagonal. When we take 3 off the diagonal, we end up with this expression, and always our b vector over on the right hand side is going to be the 0 vector, and now we need to find out what values of x1 and x2 will satisfy this. We're not going to get cases that have only a single solution. All of our solutions that we need to find are going to be infinite, and so there's a direction, and we need to pick a vector that corresponds to the direction. I'm going to solve this system of equations by finding the augmented matrix and solving it then by Gaussian elimination. So here's the augmented matrix. We apply Gaussian elimination. That allows us to set up this value, and what we're going to always try and do is take the last term here in two-dimensional space. X2 is the last term, we're going to set that arbitrarily to be 1 in three-dimensional space. I'll say pick x3 to arbitrarily be 1. But if we set x2 to be arbitrarily 1, then our eigenvector associated with the eigenvalue 3 is then found to be 1, 1. And that's just from the solution to this system of equations. But we still have another eigenvector to consider, and here for lambda equals 1, we take 1 off the diagonal, and then that reduces to this system of equations, which we can represent in augmented matrix form here. And that reduces through Gaussian elimination to this version, or simply stated, x1 is equal to minus x2. And then we'll arbitrarily select x2 as 1, which allows us to have the eigenvector associated with the eigenvalue 1 to be this column vector here. Minus 1 and 1 are the components. So that's a very simple case, and it took me 3 slides to get through. So you'll need to get used to the fact that these problems take a bit of time to address. But one thing that's good is that now you've seen the pattern. Once you get started on the pattern, it's always the same steps. So this is a module where getting used to understanding how to address these with the examples is going to be your best bet. So let's turn our attention to some example applications. This is really the topic taken up in 8.2. And I'm going to introduce a couple different topics that are probably most useful to civil engineers, geologists, geological engineers, general engineers. We'll start with remote sensing. So here's a case where what we're really taking advantage of in eigenvalues and eigenvectors is that in our multidimensional space, eigenvalues and eigenvectors are helping us address the magnitude and the directionality of data in our multidirectional space. So consider an image or multispectral data with brightness values on multiple bands of reflected light. So for different wavelengths, you're going to get different amounts of signal or different brightness values for each of those bands. And we might have, in multispectral, you might have 7 or 8 bands. You might have hyperspectral data with hundreds of bands of information. But for now, let's just consider 2 bands of data. And your data, when you look at it in geospatially rectified form, is you're looking at everything in an XY grid. But if you bring those into the dimensional space of looking at one band versus another band, your data might plot as a cloud, shown something like this. Why would you want to consider your space like this? Because whatever your target is, vegetation that's threatened or not healthy or very healthy might plot at one end of this band of data. So if you're looking at your band of data and it plots something like this, you might find that something meaningful plots at one side, whereas conditions of the opposite sort plot at another. For whatever that is, we want to consider the data then in this directional space. So you'll want to know the dimensions of this. So if you have a very elongated cloud, you'll have a sharp difference in your eigenvalues, and you'll want to know the associated directions in your space that you need to consider your data. So you'll want to know the eigenvalues and eigenvectors of your data. If you've taken a class on remote sensing, you probably know these as principal components, and you probably have used those where you just have to press a button on multispectral or on multispectral data, and you can find the principal components. This is what the computer application that you're dealing with is actually applying. Now let's consider a application from stress analysis, where you might have the stress measurements that are obtained as shown on the left. But if those are, for example, measured on the in the metal body of a component that you've built to understand whether that component is going to survive or not survive, you're not going to be able to make the decisions in the space shown on the left. You'll need to transform to the space on the right. To do that, you'll need to find the eigenvalues and the eigenvectors, and if you want to decide whether or not your component will rupture or survive, you need to look at the space shown on the right to make that decision. Now let's look at examples in this module.